we're asked to solve for the diameter of a rod, so I'm going to assume it's circular shape. I'm going to go ahead and draw this rod here. If it's 16 feet long and has 5,500 pounds of force, and it elongates a quarter inch, and it has an elasticity of 598,000 pounds, or pounds per square inch. So given this information, find the diameter. Okay. So we got 5,500 pounds going downward, and I like to draw a picture as I work, just so I can picture it. And then let's go ahead and elongate this a little bit. Let's give an elongation of a quarter inch. So this stretches it out a little bit of 0.25 inches. And we know the elasticity equals 598,000 pounds per square inch. Then it wants to know, well, what is this diameter here? What is the diameter or the thickness of what I'm going to assume, since this is diameter and a rod, of this circular rod? So I'm going to go ahead and draw the cross-sectional area here. I'm going to draw it as a circle. And I'm going to label it as cross-sectional area, or CS area. And what we want to know is, what is the diameter? Well, let's start with what we do know. We know it's 16 feet right over here. So that's the original length. And since everything else is inches, I'm going to go ahead and convert this to inches as well. We get 192 inches. Well, we know there's a force of about 5,500 pounds. We know there's a stretch or an elongation, so I'll draw this little cherry, of about a quarter inch, so 0.25 inches. And of course, we know the elasticity is 598,000 pounds per square inch, or PSI. And so now that we made a list of what we do know, I like to also make a list of what we don't know. We don't know the diameter, obviously, that's why it's asking for it, but we also don't know the area. You might say, well, how do I know? I got to look for the area. And the answer is, I don't know if I need it, but I might, so I'm going to add it to my list. And if I look at all my other symbols and units, I mean, I don't know. I don't know what stress is, and I don't know what strain is either. You might say, well, how do I know I need that? Well, I don't, but I might. So I'm going to write down the things I don't know. And so now let's look and see which one of our formulas we can use to solve for diameter. And if we look here, diameter is not actually in here, but if you notice, pi r squared is. And so I think I'm going to need to find my area. Area equals pi r squared. And we might say, well, what does that have to do with diameter? Well, we know that diameter equals 2 times r. It's double your radius. So if I can find my area, then I can find my diameter by using my radius. Well, how do we find our area? Well, there's a couple of equations with area. The first one is stress, or shear stress. But they both require that I know what stress is. I already know the force, but I don't know the area, so I cannot go this route. The other formula is our formula for elasticity, and we know all of these values except area. And so I'm going to write out this formula, which says E equals force times original length divided by area times my change in length. And I have a choice between plugging in all my numbers now and using algebra to solve, or using algebra in the beginning and then plug in my numbers later. I'm going to use my algebra in the beginning. So I'm going to multiply by A on both sides. And so what this gets us is it gets us a new formula of E times A. And you might wonder why I multiplied by A. Well, if you look, the reason why is because I wanted to get A by itself, but I also don't want it on bottom. I don't want to know what 1 over A equals. I want to know what A equals, so I want it on top. But I set it equal to force times original length divided by my change in length. And now to solve for A by itself, I'm going to divide by E on both sides, so I put E on bottom. And so my E's cancel out on the left, and we're left with a formula where essentially A and E just changed places. And so now I just plug in my values. Well, my force is 5,500 times my length, which is 16 feet or 192 inches, because everything else is in inches, and we multiply that by the change in length, which is 0.25, times our elasticity, which is 598,000 psi, and I'll go ahead and extend this. And I'll save you the math. What we end up getting is area equals 7.064, around about, inches squared. And you might say, well, that's the answer, right? And the answer is no. We need to use this to get D. And so how do we do that? Well, we read our equation. A, which is actually just what we're going to say A, is 7.064. Well, that's equal to pi times r squared. Then we need to find our radius so we can find our diameter. And so to do that, we'll divide by pi on both sides. Let me pick a different color here, but we get 2.25. We actually get like 2.2495, but I'm going to go ahead and round that to 2.25 inches squared equals radius squared. And then we're going to divide or take the square root of both sides to get what radius equals. We get radius equals about 1.5, almost exactly 1.5 inches squared, which we then plug into this equation right here to get our final diameter of 3 inches. So this rod is 3 inches thick. And that's our final answer. That's what it asked for. So how do we do it? Well, first off, we didn't use this equation. We didn't need to know that. But we didn't need to know. What we needed to know was 3 equations. We needed to know, well, elasticity equals this. Then we needed to know that area equaled pi r squared. And then we needed to know that diameter is 2 times r. So this actually needed 3 equations to solve.